Now we will move to the next speaker. That is, sorry, now it's my timer. And Klas Hagberg from Sweden. And actually he was the coordinator of our European project. And I think he will present some of the results. And after, it will be Jean-Luc Coulommiers from the FCBS in France that will talk about design.
Thank you very much. And yes, I will talk about silent timber build and the results. It has been I have had the pleasure to coordinate this project. It was a quite big project. We had around 2 million euro to spend for 3 years. I work as a consultant in WSP, it's a big consultancy group, but for this I work for RISE, the Swedish Research Institute, and have the pleasure to work for them for several projects now, and it's a real good cooperation. What I will talk about is a little bit introduction about, fill in a little bit what I have talked about before, overview on challenges for wood, a little bit about materials and system, design idea, what we have developed or some of the results in silent timber build, and I will try to summarize a little after. So just to introduce, I think wood is quite good for the future. We have heard it. There is a lot of potential, and we save a lot of carbon dioxide and so on. And it's really increasing in the market share. But I think, at least I'm convinced myself, that we need to be able to predict sound insulation prior to really develop, because we cannot just take chances. We say it should be okay, but we need to have a little bit more precise prediction. And for acousticians, we trust mainly in measurements. So it's important to have some basis measurements to know that the modeling is quite okay. That is a little bit, I will give you an idea of silent timber build, and I have had the pleasure to work with a team of researchers from Sweden, Norway, Finland, Germany, France, Austria, Switzerland, Belgium, and Italy. Many of them are here today. Just some statements. Acoustics, I would say, not always perhaps, but quite often it decides the dimensions of a floor assembly. Not only for wood, but also for concrete. Why is it 250 millimeter concrete in the floor and 200 millimeter concrete in the wall? Hollow concrete normally 265. This is of course Swedish or Nordic normal dimensions, but it's mainly because they want to fulfill the acoustic requirements. Not because they have to have it because of statics or fire, it's because of acoustic requirements. The same is that we need to, for sound class B in Sweden, it's a sound classification standard. And for wood, you need a little bit thicker. You saw on Bart's pictures here that it's quite a lot of layers, and you have to build it. Normally you end up in 500 millimeters, or slightly less perhaps, depending on how you design it, but it needs to be quite thick. So it is always the acoustics, not always, but I exaggerate perhaps a little bit, but I think it's quite often. And impact sound, you heard, it's the most important thing when you really push in force into the floor structure. It creates low frequencies, which is very tricky to remove. But I agree with Bart, it's really possible to build, no problem. Just have to think in the right way. This is a typical impact sound insulation curve. You have the frequency on the horizontal axis, and you have the sound level on the vertical axis. And the standard we are using in all over the world, it's ISO 717 to evaluate the results. And you consider frequencies from 100 Hertz up to 3150 Hertz. The rest is you don't really care about. You start to care about it, but before it has not been really bothered anyone, because you build in concrete, and concrete is really okay below 50 Hertz or below 100 Hertz. It will be okay anyway. And the only thing you need to make sure that you will not have high frequency problem. For wood, it's different. In Sweden, we introduced already 1999 requirements, mandatory requirements for 50 hertz. I don't know if it was because I was working for the National Board of Housing, Building and Planning at this time, so I had the possibility to put pressure and said, you have to do it. You release the requirements for fire and everything, but why don't you do anything with sound? Because you completely change the rules when you allow wood instead of concrete in high-rise buildings. So, but we're still the only country, I think, in the world having requirements on 50 hertz. And now we almost talk about maybe it's necessary to go to 20 hertz, but I'm not convinced myself. But it's some research going on now that say that you have quite high levels in these frequencies also. It might appear, and now it's close to be vibrations and so on. I will show you why it's like this. We have some research that was prior to the silent timber build, ACOULITE and ACOUWOOD and some other projects. We made some survey in buildings to see how is the annoyance. The annoyance here is on the vertical scale, and the sound level is on this. And when you use the ISO evaluation from 50 hertz, you reach not better than 32% of correlation. And let's see if we just check what is the levels at 20 to 50 hertz. We just don't care about anything above 50 hertz. Then we get suddenly a correlation of 78%. So what I want to say with this is it is quite important to really consider low frequencies. And if you do that, it's not very tricky to reach good constructions, but you have to take care of it. It's also to combine vibrations and low frequency sound when you design. So what are the challenges? Maybe we should turn it into opportunities. We have to think what we are doing. We should use the best system for each application for the right price. We should have the right basis for modeling, comparing results with measurements. Modeling impact sound is really the main focus, and it's also the most tricky part. So when we started the silent timber build, we were thinking, how should we compile results from sound insulation to see what is the normal levels? So we started to try to make a grouping. But what we have, this is just a small sample of all the typical constructions all over Europe. It's much more. And what we tried is to really collect as much as possible and to group these constructions to have some basis for when you have this type of construction, we arrive approximately in these levels. And at the end, we had some sort of results. When modeling, we divided them into 4 groups and a lot of different subgroups. And when we did that, we can have some agreement between the mass per unit area and the impact sound level of the floor structure. And what you see here is group A, B, C, and D. Wood joist, hybrid wood joist, massive wood, and hybrid massive elements. And what we mean with all these different letters is floor stiff, ceiling stiff, floor stiff, ceiling resilient, and so on. Floor stiff, ceiling none, it means they are completely decoupled. And all this separation we had to do to make some agreement between the measured value and the group. So how can we use this then? The idea is to, since we are a little bit not super secure when we model, we have also in this project developed, or I wouldn't say developed, but we have further developed a software called SEA Wood, which you will hear more about later, I think. But we are using this, but to be sure, we need to compare with some sort of measurements to confirm the results, to verify the results. So here you can make a first estimate depending on which group you are and depending on which type of subgroup you belong to, and see, am I on the right track when I model? So here is some examples. When we have a typical floor assembly like this is very common in Sweden or in Norway, or in Sweden and Norway, I would say. Volume elements, separated, quite light structures. And when you're using the grouping, this should be around 50 to 55 dB. And here is a result using modeling with SCA wood, 53. And now you say, but these curves, they doesn't fit at all. No, and I agree, actually, it doesn't fit at all. But it also mirrors a little bit the complexity. And I don't know what is the right one, if it's the measured value or if it's the calculated value. But at least we know that we are approximately in the right single number value. Why I say we don't know what is the right? When you make a measurement, you put the hammer machine, the impact sound machine, somewhere on the floor. You don't know if you put it on the joist or in the middle of the field. So it's quite tricky, and you can have different results. At least when you calculate, you know where you put the force. But anyway, we know that we are a little bit, at least close to the reality. And here is a similar floor structure that was shown by Bart before. We had cooperation with another project called HCLTP, where they were developing hybrid CLT floor structures to be with long span, and they didn't know how should we make sure that they also provide a good sound insulation. So they come up with a proposal, and we modeled it to 57. It's not super good, but it's perhaps good enough many times. But they wanted us to see what can we do to improve, and we did a little bit same as Bart. So we moved the resilient layer and only one resilient layer, and we could arrive in 4 dB better, and 4 dB is quite a lot better actually in this kind of floor. What we also did, we were changing a little bit the height of the beams and the distance between the beams. Yeah. So, of course, we don't know if it's the truth because it's just a model, and we didn't really build this floor, but we think we are almost on the right track. So the design idea: estimate sound, impact sound, create a model. You can, after you have created a model and you know that you are right on track, you can actually change some characteristics, change some different materials in the floor structure, and improve the model. And you can be quite sure that you are on the right spot. Calculate airborne sound. I would say that we are more precise. Okay, I have to hurry up a little. And we have to estimate flanking. Flanking, we are not really, there is much more to do with flanking. We have done some measurements, but we are not all the way through yet. But everything will be presented in 4 reports, which are almost ready. They will be available on a website as Silent Timber Build. I will fast go through this one because it just describes what we are doing. You will hear more about the atlas that we have developed and the design guide. Summary. I think we have come through to make a more optimized solutions. It will be really much more safe to make calculations. And like I told you, there will be a report series that can be downloaded soon from this website. And thank you very much for listening. And thank you to all my team in Silent Timber Build. It has been fantastic to work with you and all the people who are funding all this project. Thank you.